Okay, thank you very much, Randy. And I want to thank Randy and ASU for inviting me here. I'm very pleased to be here, talk about a subject about which I feel a great deal of passion, failure mode effects analysis. Before I start, who's heard prior to this title, who's heard of FMEA, failure mode effects analysis? A couple of people. Anybody done an FMEA? All right, thanks. As Randy mentioned, I've worked with a lot of different companies. I'm not a biologist, so I want to state that right up front. I'm an engineer by background, worked with a lot of companies on reliability and quality methods. I think we have an opportunity, but with all humility, I want to go through the process, and then it's going to be feedback from people here and at the workshop to see how fruitful that opportunity is. Let me start on the next slide with a little bit of humor. This is a story that is got some interest to it. In 1895, there were only 2 cars in the entire state of Ohio, and they collided. So it's often called Murphy's Law. Murphy's Law, if anything can go wrong, it will. The lesson, yes, the lesson is it pays to anticipate and solve problems before they become catastrophic. And one of the objectives of FMEA is to do that. I will provide an overview. Now we're going to condense about 6.5 hours of teaching, and I've taught FMEA to thousands of times, and so I'm going to condense 6.5 hours into 10 minutes on an overview of FMEA, maybe a little less. And then we'll have time to explore whether FMEA can be an application within evolutionary biology. I'll have an example of FMEA as part of that. And interestingly enough, the example is going to be a projector bulb. So hopefully nothing fails in the middle of this. I'll introduce evolutionary FMEA, and I've got 2 case studies that, and I've read Randy's book, Why We Get Sick, and I've read lots of articles. As part of my preparation, I needed to immerse myself in evolutionary medicine and evolutionary biology in order to talk somewhat realistically about this. So I've got a couple of case studies to put in there, then we'll summarize. So overview, one of my favorite quotes from Thomas Edison, I haven't failed, I found 10,000 ways that don't work. So studying how things fail is the subject of failure mode and effects analysis. And of course, most of the applications are in industry and medical devices, this type of thing, but it can apply in special activities such as this. Let me start with the importance of system interactions. And I believe that's a common ground here between FMEA in engineering and failure analysis in biology. Systems can be very complex. So in this example, anybody here own a General Motors car? Okay. You've heard, very smart. No, you've heard that a while back they had an ignition problem. And if the keys got a little bit too heavy, that ignition system would malfunction. But that affected the steering, because steering assist requires that ignition system. It also affected the airbags. So you have interactions, very complex in systems engineering. And that's one of the subjects of FMEA, because FMEA can help model these interactions so that they don't have problems. FMEA drives upfront activities. That's the normal application of FMEA is upfront, but it can model applications in service as well. Well, the cartoon here, we can save 700 lira by not taking soil tests. The application that I want to talk about here briefly, Microsoft Xbox, for example, $1.5 billion for problems that occurred when they released it originally a number of years back that they had to then pony up and pay. We talked about the ignition switch at GM. Many lives were lost. Takata airbags in many cars that some of you are still driving have problems. A lot of recalls, deaths have occurred because of it. Firestone tires years back are complex systems between the tires having the right pressure, too much pressure, too little pressure, and then the height of the vehicle, like an SUV, can create an unstable situation. So then you have a potential rollovers. And then, of course, did anybody own the Samsung Note 7? Okay. So that was a release, obviously, that had an incendiary problem. So these are the types of problems that well-done FMEAs, done properly, can address before they become catastrophic. And then the last slide here in terms of the introduction in the last cartoon is the quality and low prices, which one do you want? Well, we want both. And the FMEA helps to manage the trade-offs. Safety and reliability, I consider those must, but also costs, timing, and then you have competing requirements. Since the subject of systems engineering is how do you balance the competing requirements. So what is FMEA? Definition: a structured engineering analysis performed by cross-functional teams of subject matter experts, very important that it's team-based, thoroughly analyzing product designs or manufacturing processes or other activities, conducted early in the product development process, and then here's the key, where we try or attempt to anticipate and correct problems and weaknesses before before the product's launched, before the customer uses the product. The procedure begins with primary functions of a system and identifies, and here's the three things that it does. Identifies and fully understands failure modes, the effects of failure, and the causes of failure. Then it assesses risk related to those failure modes, effects, and causes, and prioritizes issues for corrective action. Then it carries out the corrective actions to reduce risk to an acceptable level. So those are the three things that any FMEA does. And when we talk about the possibility of FMEA being applied in this field, we want to consider those three things and see how this might work. Medical diagnosing often begins with symptoms, not always, but oftentimes. FMEA always begins with functions. Function, what the item is intended to do, its purpose. So I'm going to run through some very quick definitions for you, and then I'll carry an example on each one with the projector bulb. Thank you, Randy. Function, what the item is intended to do. Often, we always want to attach a standard of performance. So we don't just say it's intended to do this, we say to what standard of performance. And they're typically defined verb-noun, and there can be many functions for each system. Projector lamp example. Now an FMEA runs across, it's like a two-dimensional spreadsheet type of analysis. It can be three-dimensional, but I'll just show it to you as two-dimensional. It has different columns. First column is function. This example, provide reliable light image transfer at a minimum of 1,000 lumens for 2,000 hours of operation. So we got what it's intended to do, and we include the standard of performance. The next column of an FMEA are failure modes. Failure mode brings together two terms. Failure, which is the act of ceasing to function or the state of not functioning, and then mode, which is the manner in which something occurs. So when you put those together, failure mode is the manner in which the item potentially fails to meet or deliver the intended function. That's by definition. And there can be many failure modes for each function, and often are. Example here, lamp burns out prematurely. So function, lamp's supposed to provide a certain number of lumens over a certain period of time, burns out prematurely would be an example of a failure mode. Now once you've identified a failure mode, we take a look at what the effect of the failure is. So now we're talking about the consequence of the failure, always brought up to the system or end user. So even if it's a projector bulb that burns out prematurely, we want to look at what is on the projector system, or if your system includes the streaming, the bulb burning out will have some effect overall on the system and end users. It can be a single description at that end, or you can actually trace it. Here's what happens, here's what happens, here's what happens, and that's important, that traceability. Severity is one of three risk assessments in an FMEA. Severity says, on a scale like of 1 to 5, how severe is the effect of the failure. Going to the next column then, example, no light on image, customer dissatisfied. Pretty simple. We now move to cause. So failure modes have causes. Failure modes have effects and they have causes. Cause is the specific reason for the failure. Oftentimes we'll ask why and then ask why again. We'll get with the subject matter expert team. In fact, Toyota uses the 5 whys where they ask why 5 times. I don't think it has to be 5, but it could be 4, 3, 2. Get to the root cause, particularly for high severity problems. That's part of the fundamentals of FMEA. There can be many causes for each failure mode. For high risk problems, cause should be taken to the level of failure mechanism. And then once we've got the cause identified, we're going to say how often does it occur, again on a scale like 1 to 5, where 5 would be very often and 1 is it's not going to happen. The failure mechanism, here's where we can draw from engineering literature, and we're going to get the chemical, we're going to get the mechanical, thermodynamic, electrical mechanism of failure. Or at a complex system, it's the process of degradation or chain of events leading to and resulting in particular failure mode. So we're tracing from cause back to failure in failure mechanism. I think that's an important common ground between the engineering application and evolutionary medicine. Controls and detection are an important part of FMEA. Controls are the methods that are planned to control the failure mode and associated cause. An example in biology would be treatment. So you have certain controls that are planned or in place. Treatment protocol would be an example. Then once we've identified the controls, sometimes they're prevention controls, sometimes they're detection controls to discover the problem. Once we've identified that, we ask the question, how likely is the protocol that we have to detect the cause of the problem? And that becomes the third risk criteria, again on a scale of 1 to 5. So we got severity, frequency, and detection risk. An example here of cause, inadequate voltage to lamp due to corrosion of base. Corrosion is the mechanism of failure. It can be modeled scientifically. We can actually model and thereby predict the frequency of it. And then an example of controls might be some test. You might run the lamp or the projector system through some testing protocol. So the risk assessment then brings together the severity risk, which is that's how severe the effect is, the occurrence risk or frequency risk, which is the likelihood of the cause, and the detection risk, which is the likelihood that the protocol will detect the cause. And risk then can be prioritized, and you can set up algorithms that say, based on severity this, occurrence this, detection this, it's super high, medium, low, or anywhere in between in terms of risk. Then the last primary set of columns in the FMEA are recommended actions. So we take a look with the subject matter expert team and say, now that we understand this, what are the tasks that we're going to do to reduce risk to an acceptable level? So now you've had a 6.5 hour condensed into a few minutes of what an FMEA is. Recommended actions example, change the lamp base to some material to be less corrosive, or modify the testing, or revise the interface between the bulb base and the connection. Very important that we use multiple recommendations and multiple tasks. This is what I teach. When you have high risk, it always takes trying to reduce severity, trying to reduce occurrence, trying to reduce detection risk. Okay, so in summary, we bring together the best thinking of a subject matter expert team. We analyze primary functions for their failures and consequences and causes, and we assess risk, and then we recommend actions to reduce risk. Okay, so the question then becomes for us is, can FMEA be applied to human biology or evolutionary biology? And of course, this shows you that I have read Randy's book and his other literature. Let me take 2 slides and talk about the mapping of FMEA possibility. So I'm bringing this together to you as an opportunity. Evolutionary functions, and I'll do 2 case studies on this, which we won't have time to go over in detail, but are available now for the workshop itself. Evolutionary functions, They have their own definition, which I don't need to explain here. The ultimate cause, evolutionary species, attaches there. Analysis of trade-offs. Then we go to failure modes, the vulnerabilities. Then we go to contributing risk factors and type of vulnerability. So we basically attach those to the failure modes. And here we can get the 6 types. What type of vulnerability is it? Then the effects and severity risk. So the consequences and symptoms. Second slide, proximate cause at this point. So what are the proximate causes? Now we're at the immediate and individual level. And now we can get to the frequency risk of those causes. Here's where we can attach the mechanism of failure, the disease category, the different types of categories of disease, the treatment protocol, and the risk of that treatment protocol, and then what are the interference consequences. Then we can get to overall risk and then recommendations for research or recommendations for follow-up. So 2 case studies, for example, morning sickness. Pregnant woman experiences nausea or vomiting during pregnancy as a mechanism to avoid potentially harmful toxins. So that would be an evolutionary function. Then we take it across, and I promise you I won't go over every column here because of time, but this is available and we can talk about it as a case study. It's not perfect because I did it and I'm not a biologist. I did it based on the reading that I did. But it does line up in columns and you can organize, and the benefit is all the information's in one place that relates to this, and we can adjust the columns, the column headings, which I hope we can do over the next day and a half. Then you come through, you get the overall risk and interference consequences, and then recommendations for follow-up action, what research you want to do, et cetera, okay? And then the second case study is enable this, now the febrile response or fever response, enable core body temperature to increase up to a certain level that's not dangerous for a short period of time to fight infections. And then again, that can be followed through with the evolutionary causes and trade-offs and all the information up to research when is fever useful or not, for example. So evolutionary FMEA summarizing using the structured approach of FMEA to organize and analyze selected evolutionary functions, assess risk, prioritize and track research, and keep it all in a relational database. Summary, while FMEA is a proven tool to analyze products, manufacturing processes, and specialized activities, it may also be useful in evolutionary biology. So I'll bring this information to the workshop as we talk together over the next day and a half, and we can explore on what this use might be. Thank you very much. Got time for a couple of questions?
Yep.
If anybody has a question, by all means. Yes, go right ahead.
I was very excited to hear that because your talk. Because before coming to this, although I'm not going to speak, I decided to set myself the task of making something I pretentiously called on my scribbles failure theory. And I began with what I know, the medical question I know best as an evolutionary biologist. I began with the obesity question, its relationship to type 2 diabetes and cardiovascular problems. So I tried to take that and look at the huge number of articles I've read to figure out what was missing from the medical point of view compared to my evolutionary biologist point of view. And I came up with almost exactly the same list of things that you went through.
Great.
But there's one thing that in the medical research literature is lacking or faulty in my impression, that you don't have to worry about. And that is the identification of the primary failure. Because, I mean, what is the trait that you put your interest on? So you automatically have it, I think. Because, for example, an airbag or a switch, I mean, you have a good focus. In the medical literature, they sometimes confuse symptoms, which are sometimes called risk factors, and that risk word doesn't mean probability of occurrence, it means symptom. So they get, my impression is that often they're distracted onto looking at the wrong pathways. And you included what evolutionary biologists would call ontogeny, the development of, because you wanted to look at the different stages of the failure. And what you're calling function, we would call simply adaptive function, that is evolved function, what formed it, what designed it under natural selection. So I was just excited.
Great.
Because I could take the terms I had in my little failure theory and just make synonyms from what you were saying.
Thank you very much. Appreciate that. Got another question there, Pete?
Jay's been raising his hand. Or Pete. Okay.
Yeah, thanks, Carl. Yeah, just adding to that point in a way, but as you were talking through what FMEA is, I was thinking, well, the key difficult part for you is doing the anticipation of the problem, a key falling out of an ignition switch because it's too heavy or something. It's difficult for people to spot that ahead of time, whereas when we're looking at evolutionary medicine or medical problems, we've already seen that there's been this problem, so we've effectively already had the key fall out of the ignition switch. And so it seems to me almost like we're working backwards. We're kind of going through these phases, but in a different direction to the trying to anticipate problems before they've happened. They've already happened, we're just not quite sure what the causes were. I don't know if you've got a response to whether you see us in a different order now.
Yeah, it's a good observation, Pete. Oftentimes, like I work with, for example, Apple or Tesla and different companies, and new technology comes out, and we're trying to anticipate what that new technology will do in terms of failures. But we also use FMEA on current applications. You have, oil and gas platforms or solar applications, things that are already in the field, so to speak. And then we say, let's bring together the field history where we've seen failures in the field, and let's say, how can we better understand those failures? How can we understand the causes of failure, and how can we put in place protocols that minimize the risk? So it actually does more than anticipate. Part of it is anticipation, but also how do we mitigate risk based on what is already currently occurring? Good observation. Yes?
As biologists, particularly on the medical side, we don't have the luxury of designing the system.
Right.
What we have is just trying to engage, the complexity as we find it. We're always searching for something simple, only to find out for the things we most care about, it's not simple at all.
Right.
I mean, that's our common kind of reflex, and whether it's cardiovascular or whether it's obesity. But just as a little thing, you brought up nausea as a pregnancy-related nausea. And you would think the way you described it there, and my wife, by the way, for 2 pregnancies had 9 months of nausea. And my mission from my wife was to go out and figure it out, only to find out that A, very little was known about it, and B, there really wasn't much you could do about it except for me to go down to the common store and bring back, these ice chips, to cover it. Now, the common view is that it's a toxin. You're trying to get rid of it, and that's the biological so-so story, But so-so stories, as we all know, run forever, And you threw it out there as if it was like a fact, the admission, because it's a common sense assumption. What else could it be for?
Right.
It might not be for anything. Right? Just a simple artifact that happened to get co-expressed in something. So where does that figure? So the engineer comes in thinking that there's always a design principle.
Yep.
A lot of my colleagues always assume that. Like the visual system is just this. Biology is a lot of slush.
Yep.
And
just to comment on that, and I agree with you, is that's why it's important for us to do this with the right teams. Because the teams will determine what is the right description of the evolutionary function. They will determine what the right proximate causes and other columns are, and the risk, and then the follow-ups. Because you're correct, we can't just assume it's this, that it has some value because it's there.
We're going to do just one more, and then we'll move on to our next speaker.
Okay, thanks, Carl. I really enjoyed that. One of the things in which your engineering differs from the biology is in biology we very often don't know as much about the mechanism that produces either health or disease or failure, or how it operates under normal conditions. Is there a way around it? Is there a way to approach incomplete knowledge of a system?
Yes, and I understand that, and that is often the case even in industry. But what I suggest there, and we can talk about it in the workshop time, is that if we get the risk identified for the high-risk areas, the recommended actions column is where do you need to put the research to understand the mechanisms. So you prioritize your research. University of Maryland does this on what they call failure mode mechanism and effects analysis, which I collaborated with one of their professors on, and that prioritizes their research projects for modeling failure mechanisms. So that's